Something strange is happening at the top and bottom of the world, almost at the same time. And the strange part isn't simply that the polar ice is changing, it's how differently it's changing. In the Arctic, a decades-long pattern has suddenly behaved in a way researchers didn't fully expect. In Antarctica, an entirely different ice system is responding to a completely different set of forces. And when scientists started investigating what was happening, they uncovered discoveries that sound almost impossible. A hidden island, a massive underwater breeding colony, ancient air trapped inside Antarctic ice for millions of years, and beneath the continent itself, an enormous geological structure hidden under the ice. But here's the part that matters. I'm not starting with those discoveries because the discoveries themselves aren't the biggest mystery. The bigger question is why we're seeing all of this now, and what these changes reveal about how little we still understand about the most remote places on Earth. So let's start at the top of the planet. For decades, the Arctic appeared to be following one of the clearest trends in modern climate science. Sea ice was declining. Satellite measurements going back to 1979 showed the long-term direction clearly, especially during the summer minimum. Year after year, researchers watched the ice retreat. So the expectation seemed straightforward. As the planet continued warming, Arctic sea ice would continue declining. But then something unexpected appeared in the data. The rate of decline didn't behave like a perfectly straight line. For roughly 2 decades, researchers observed periods in which parts of the Arctic sea ice record appeared to flatten or slow. At first, that might sound reassuring. It wasn't. Because a temporary pause and a permanent reversal are two completely different things. And the newest research suggests the Arctic's apparent stability may have been more complicated than it first appeared. Recent measurements have shown extremely low winter sea ice conditions, with the 2025 and 2026 winter maximums sitting near the bottom of the satellite record. But here's where the story gets interesting. Scientists aren't simply asking how much ice disappeared. They're asking, why did the system behave this way? Because Arctic sea ice isn't controlled by temperature alone. Wind matters, ocean currents matter, snowfall matters, clouds matter, the temperature of the water underneath the ice matters, and the timing of all those factors can determine whether the ice grows rapidly, slowly, or barely at all. That's why a short-term change doesn't automatically mean the long-term trend has disappeared. The Arctic can slow down. It can temporarily recover. It can suddenly lose a huge amount of ice. And then it can stabilize at a completely different level. And there's a mechanism sitting underneath all of this that makes the Arctic especially sensitive. It's called albedo, and it creates a feedback loop that can make the original problem worse. Ice is bright. It reflects a large portion of incoming sunlight back into space. Open ocean is dark. It absorbs much more of that energy. So when ice disappears, darker ocean water is exposed. That water absorbs more solar energy. The ocean warms. That makes it harder for ice to form. More ice disappears. More dark water is exposed. And the cycle continues. It's one of the reasons the Arctic has become one of the fastest warming regions on Earth. But here's the important part. The Arctic isn't the only pole behaving unexpectedly. And the other end of the planet has a completely different story. Antarctica is not simply a giant version of the Arctic. The Arctic is primarily an ocean covered by floating sea ice. Antarctica is a continent covered by an enormous land-based ice sheet. The difference changes almost everything. For years, Antarctica seemed strangely resistant to some of the changes happening farther north. Its surrounding sea ice behaved differently. Its winds behaved differently. Its ocean circulation behaved differently, and scientists spent years trying to understand why. Then the pattern changed. Antarctic sea ice began falling sharply. Record lows appeared, then more record lows. And suddenly, a system that had once looked relatively stable was showing signs of much greater volatility. Researchers investigating the change identified several forces working together. A warming ocean surface, changes in southern ocean circulation, shifts in powerful winds surrounding the continent, and warmer water moving upward from below the surface. Individually, these mechanisms are important. Together, they can reinforce each other. And that's what makes Antarctica so difficult to predict. But there's another layer to the story. Because scientists weren't just seeing changes around Antarctica, they were seeing changes inside the ice itself. Satellite measurements using gravity data detected a surprising development between 2021 and 2023. After years of mass loss, the Antarctic ice sheet experienced a period of measurable mass accumulation. Researchers described it as a significant reversal. But this needs to be understood correctly. It does not mean Antarctica has recovered from decades of ice loss. It does not erase the long-term trend. And it doesn't prove that the ice sheet has permanently changed direction. It was a short-term shift. But it was a real one. And that's precisely why scientists found it interesting. The polar climate system isn't a machine that moves smoothly in one direction. It fluctuates, sometimes dramatically. And those fluctuations can reveal processes that aren't obvious when you only look at a decades-long trend line. But while researchers were measuring these changes from space, Something else was happening much closer to the ground. And that's where this story gets truly strange. Earlier this year, researchers aboard the German icebreaker Polarstern were operating in the Weddell Sea. The expedition was studying the Antarctic environment, including ocean currents, sea ice, and ecosystems beneath the surface. Then researchers encountered something unexpected. An island, not a newly formed volcanic island. Not some enormous landmass rising dramatically out of the ocean. A small landmass that simply hadn't been properly mapped before. Older nautical charts had indicated a vague danger zone in the area, but researchers determined that there was a distinct island there. Think about what that means. We're talking about Antarctica, a region that has been studied by scientists for generations. A region covered by satellites, research vessels, aircraft, radar systems. And yet, a piece of land was still sitting there without being properly represented on the maps. But that discovery would soon look almost ordinary, because the researchers weren't finished exploring. They turned their attention beneath the water. And that's when they found something much bigger. Scientists lowered an enormous underwater camera system toward the seafloor. They weren't expecting to discover the largest fish-breeding colony ever recorded, but the camera kept revealing nests, and more. Eventually, researchers realized they weren't looking at an isolated breeding site. They were looking at an enormous ecosystem. An estimated 60 million icefish nests spread across the seafloor. 60 million. A breeding colony on a scale researchers had never documented before. And here's the part that should make you stop for a moment. This wasn't discovered because scientists had perfectly mapped the region and then decided to investigate the colony. They found it while studying something else. An enormous ecosystem had been sitting beneath Antarctic waters, largely unseen. And suddenly, an important question emerged. If something containing tens of millions of nests could remain hidden in a region scientists have been studying for decades, what else are we missing? The answer may be buried much deeper. In East Antarctica's Allan Hills region, researchers drilled into ancient ice. But this wasn't ordinary ice. Inside it were tiny pockets of ancient air that had remained sealed for approximately 6 million years. Think of what that means. Every bubble contains a tiny sample of Earth's ancient atmosphere, a frozen snapshot of a planet that existed millions of years before modern civilization. Researchers can analyze those gases and compare them with evidence from the surrounding ice, and that allows scientists to reconstruct pieces of Earth's climate history that would otherwise be almost impossible to access. The ancient record also revealed something intriguing. Earth experienced major cooling over that period, while changes in some greenhouse gases were comparatively modest. That suggests the climate system was being influenced by several powerful mechanisms at once. Ice, ocean circulation, surface reflectivity, atmospheric changes, and the movement of heat around the planet. In other words, the climate system was complicated millions of years ago too. But the strangest discovery wasn't trapped inside the ice, it was underneath it. Stand on Antarctica today, and you see an enormous white landscape. But beneath that white surface is an entirely different world. Ancient mountains, basins, faults, valleys, and geological structures buried beneath kilometers of ice. Recently, researchers studying East Antarctica combined radar, gravity, seismic, and magnetic data with models of the underlying terrain. And they identified something remarkable. Features that had previously been studied individually appeared to form part of a much larger geological structure, a massive continent-scale radial pattern extending beneath the ice. The structure appears to have been shaped by deep tectonic processes operating long before Antarctica became covered by its modern ice sheet. And this isn't just an interesting geological footnote. The landscape beneath the ice can influence how the ice behaves above it. Basins can hold subglacial water. Bedrock geometry can influence ice flow. And hidden geological features can affect the stability of portions of the Antarctic ice sheet. So researchers aren't mapping this ancient landscape simply because it's fascinating. They're trying to understand how the ground beneath Antarctica could influence what happens to the ice above it. And now we can finally return to the question we started with. At first glance, it might seem like they are. The Arctic is changing. Antarctica is changing. Both are experiencing unusual conditions. Both are producing unexpected scientific discoveries. But there is no evidence that the Arctic is directly causing what's happening in Antarctica. The two systems are physically very different. One is an ocean surrounded by continents. The other is a continent surrounded by ocean. Different winds, different currents, different geography, different feedback mechanisms. So the connection isn't a mysterious signal traveling from one pole to the other. The connection is much more fundamental. Earth is gaining heat, and that additional energy is interacting with each polar system according to its own unique physical conditions. In the Arctic, the response is strongly influenced by sea ice loss and the albedo feedback. Around Antarctica, ocean circulation, wind patterns, freshwater, atmospheric systems, and the geometry of the ice sheet all play major roles. Same planet, different mechanisms. And that's why two places experiencing the same broad warming influence can respond so differently. Whenever a short-term ice increase appears in the data, someone will inevitably claim the ice is recovering. And whenever another record low appears, someone else will claim the entire system is collapsing. Both reactions can miss the bigger picture. A short-term increase doesn't erase decades of ice loss. And a single record low doesn't mean every part of Antarctica or the Arctic is behaving identically. The scientific record is more complicated. Long-term trends and short-term variability can exist at the same time. That's not a contradiction. It's normal for complex physical systems. Imagine looking at a mountain road from far away. You can clearly see that the road is climbing, but if you zoom in, the road contains hundreds of turns. Some sections climb sharply, others flatten, some even dip slightly. The overall direction hasn't changed, but the path isn't a straight line. Polar climate systems work in much the same way, and that's why scientists keep measuring them, because a temporary change can reveal something important about the mechanisms operating underneath the long-term trend. There's another misconception worth clearing up. When floating sea ice melts, it doesn't directly cause a dramatic rise in sea level. That ice is already floating. The bigger sea level threat comes from land-based ice, glaciers, ice sheets, ice resting on solid ground. When that ice flows into the ocean and melts, water that wasn't previously part of the ocean is added to it. That's where the major sea level consequences come from. But sea ice still matters, because it influences the energy balance of the planet. Less reflective ice means more dark ocean. More absorbed energy can warm the ocean. And warmer ocean conditions can eventually affect nearby glaciers and ice shelves. In the Arctic, changes in sea ice can also influence atmospheric circulation and weather patterns. So something happening thousands of kilometers away can eventually influence conditions much closer to where people live. The poles aren't isolated from the rest of Earth. They're part of the same connected climate system. Scientists aren't simply looking backward, they're watching what happens next. In the Arctic, one major question is whether the recent extremely low ice conditions settle into a new lower range, or whether natural variability allows a stronger recovery. In Antarctica, researchers are watching the interaction between ocean temperatures, winds, sea ice, and atmospheric circulation. They're also watching extreme events, because the most concerning possibility isn't necessarily one extraordinary year. It's the repetition of extraordinary years. One unusual event can be explained by natural variability. But if similar events begin appearing repeatedly, the statistical picture changes. And that is exactly why polar researchers keep collecting measurements year after year. Not because they know exactly what the next decade will look like, but because they know the next set of observations could reveal something they didn't see coming. Just like the island, just like the fish colony, just like the ancient ice, just like the geological structure beneath East Antarctica. After everything we've covered, it's tempting to focus on the dramatic numbers, the record lows, the ice gains, the millions of nests, the millions of years preserved inside frozen bubbles, the enormous structure beneath the continent. But there's a deeper lesson here. Scientists have spent decades studying the poles. They have satellites watching from space, aircraft flying over the ice, research vessels crossing dangerous oceans, radar systems penetrating kilometers of frozen terrain, and increasingly sophisticated computer models trying to simulate what happens next. And despite all of that, the poles can still surprise them. That doesn't mean scientists don't understand the climate system. It means they understand it well enough to recognize when something doesn't behave exactly as expected. And that's the most important distinction. The Arctic slowdown doesn't erase the long-term decline. The Antarctic mass gain doesn't erase decades of ice loss. The hidden island doesn't mean Antarctica is unexplored. The fish colony doesn't mean scientists know nothing about Antarctic ecosystems. And the ancient ice doesn't give us every answer about Earth's climate history. But together, these discoveries tell us something powerful. The polar regions are not simple. They're dynamic systems filled with feedbacks, interactions, and processes that can operate over days, decades, or millions of years. And sometimes, the most important scientific discovery is not an answer. It's realizing that the question you were asking wasn't big enough, because somewhere beneath the ice, somewhere beneath the ocean, or inside a frozen bubble that hasn't been opened for millions of years, there may still be evidence waiting to change what we thought we understood. And that is why scientists will keep watching both ends of Earth. Because the next surprise could come from the satellite data. It could come from an expedition. It could come from a drill. It could come from the ocean floor. Or it could come from somewhere beneath Antarctica that nobody has even mapped yet. The poles may be among the most closely watched places on the planet, but they are still far from fully understood. And that might be the strangest discovery of all.